Okay, we'll try to keep this one relatively brief, maybe around 15 minutes or so. I've got 4 questions to look at. Most of them are fairly straightforward. I have one that is a little different than the typical, but this is a classic question, and I tried to make it very, very light, excuse me, because, people make related rates into this big, huge, hard thing, and it's just sometimes it's not. So my question that I have for this particular question is based on our good old friend, the right triangle. Typical little question. We actually did one of these in class already, where we have a couple of trucks that are driving away from each other at some given values. Hopefully, it doesn't exactly shock you that we're looking at the 30 and the 40 sitting right there. The part that is a little bit different is that it talks specifically about 6 minutes later. And so we do have to deal with the fact that we have a little bit of a unit disparity where we're talking about miles per hour, but then we're talking about 6 minutes. But we'll kind of see how that goes. So the first thing that I wanted to do is I wanted to look at this thing and let's see, I think I wanted to say, so truck A is traveling east. So this is going to be A right here. And it says truck A right here is traveling at 40 miles per hour east. So they're giving me a little bit of information that dA dt is 40 miles per hour. Okay, so I'm going to try to color code all these things so I keep them together. Looks like truck B over here. So we're going to be looking at dB dt because they told me a little bit of information about truck B. So truck B on this side right here is looking at, it looks like 30 miles an hour. And last thing, they actually asked about how fast is the distance between them. So we could, I guess, come like this and call that C. And so dC dt, the difference between them, is really our big question that we're trying to find. Now, again, not a big surprise that we're looking at a squared plus b squared equals c squared. I do have to, by the way, deal with a snapshot in a second, but I'll get there. 2 A's dA dt, 2 B's with a dB dt, and 2C dC dt. Okay, now obviously we could go through and cancel out all those 2's because we could divide everything by 2, and that wouldn't be a big problem. We also know that dA dt is 40 and dB dt is, the dA dt right here is 40, and then we have dB dt right here is going to be 30. But we have one other thing. We need to figure out the snapshot. So if this vehicle is able to do 40 miles an hour and 30 miles an hour respectively in 6 minutes, that's exactly 1/10 of an hour. So I was being pretty nice. So again, if we took 40 miles an hour, 6 minutes is literally 1/10 of an hour. That would make it exactly 4 miles for this vehicle, 3 miles for this vehicle. And so at this, again, snapshot, as we keep calling it, we're talking about 3 miles, 4 miles, and 5 miles. So we can go ahead and throw that information in. I know that A is, of course, 4. dA dt is 40. B right here is 3, with dB dt being 30. C is 5. And dC dt is my magic value I'm looking for. It looks like I've got 160 plus another 90, or a total of 250. And we could have kept the units in as we went our way through this problem, but 250 divided by 5 is in fact going to be 50, and that would of course be the distance in time. So 50 miles an hour. And one time a little while ago, I went ahead and I made a visual for this just to kind of show what this looks like, because I think we can kind of think about it, but I did make something to kind of help us do that. And so that I have a quick little Desmos demonstration here, that we have our 2 trucks sitting there. And as they drive away from each other, you can see that although they are driving at different rates, you can see that then there's even a third rate, which is the distance between them. So that's a nice little cute little demo, no big deal. Okay, for my next question, for what I have down is question 6. This one is a little bit less typical because we usually have questions where we're dealing with nice right angles. Well, I have two fellows here that are walking away from each other on a road, just like the trucks, but the part that's a little bit different. It says that the two roads meet specifically at a 60-degree angle, which, by the way, is a constant. So we've talked before how calculus works much better in radians. So I'm going to put this constant right in here, pi over 3. So the angle between these people is definitely going to be that. The intersection, they leave, a man starts from the intersection at 1 p.m. So let's start there. At 1 p.m. It walks along the road at 3 miles per hour. So let's call this one right here A. So dA dt is going to be 3 miles an hour. So I'm going to try to keep all of these things separate so I know what's what. At 2 p.m., now that's a little bit interesting. This one leaves a little bit later. At 2 p.m., the other one works at 4 miles an hour. Now, again, you're obviously kind of seeing that I'm playing with a little bit of 3, 4, 5 here, but we'll see. It's going to be a little bit different. 4 miles an hour is going to be what happens for person B right here, but they left a little bit later. And now keep in mind that the whole thing started at 1 o'clock. At 1 o'clock, this guy is walking at 3 miles an hour. And then all of a sudden it says, how fast are they separating at 4 p.m.? Which means this person right here, if they left at 1 and it is now 4, they have been walking for a total of 3 hours. So that would mean that this person has been walking for 9 miles at this moment in time. So it might have looked like we had that little 3, 4, 5 triangle, and it may be or it may not be. I don't know. I'm going to have to see. Now, for person B, they left a little bit later. They didn't leave until 2 p.m. And so at 2 p.m., they've been walking for 2 hours at 4 miles an hour. So this, again, snapshot is 8 miles. So we need to do one more thing, and I'm going to call this thing C because that's the value between. Now, the temptation that people have is they want to actually go with that Pythagorean theorem, but this is not a right triangle. I don't have that ability. So what I need to do is use the law of cosines, which we haven't done this year at all. So anytime you have a situation like this, what we can say is C squared equals A squared plus B squared, which I know you're going, hey, isn't that the Pythagorean theorem? But we talked about this, how the law of cosines looks exactly like the Pythagorean theorem with a little qualifier because it is not actually a right triangle. So we have a little bit of extra information right here to figure that out. So we'll see what happens. So for starters, we don't want to put in C yet because it's not a constant. We can't put in A or B. It's not a constant. We do have a snapshot, but they're not constants. The only constant in this whole thing is going to be theta. So the cosine of pi over 3 right here is, in fact, 1/2. The cosine of 60 degrees is 1/2. So I suppose we could put that one piece in right here. If the cosine of 60 degrees or pi over 3 is 1/2, it's going to cancel that 2, and we're down to here. So let's see what we got. We're going to go through here and do our little story. So let's see. Oh, and we do want to go ahead and find out what the value of C is for this particular moment in time in the snapshot. So let me do that. So C squared would be 81 and 64 minus 72. And 81 and 64 is 145. Take away 72 would be 73. So C in this snapshot in time would be 73. We're going to need that in a minute. So now if we go and we take our derivatives, this is going to be a little harder than the previous one because we have this mixture right here. But we have two C's with a dc dt. And keep in mind, that's the answer we want to get with two A's with a dA dt. We've got two B's with a dB dt equals, now here's where it gets a little bit harder. We have to do the derivative of the first, which is dA dt B, and then minus dB dt A. Sorry, I'm changing my font here from uppercases to lowercases because I meant to use capitals and I didn't. So anyway, if we look through this problem, it looks like we have everything we need. We have 2 root 73 because we figured out in our snapshot it was 73. dC dt, of course, is what we wanted. A, we figured out, was 9. dA dt was given to be 3. B was 8 with dB dt up here being 4. dA dt again being 3, saddled up with a B, which was 8. And dB dt, which again right up here was 4, with A, which again was 9. Now again, there's a lot of little pieces to put together that we have to be very, very cautious with, but it's all there. Let's look at, I got 54 here. I got 64 here. I'm going to lose 24. I'm going to lose 36. I kind of noticed that these two pieces would make, 40. These two pieces right here, 54 minus 36, I think that's 18. So it looks to me like I got 58 out of all of that stuff. So I have 2 roots of 73 times dC dt. This entire side becomes 58. And so doing just a little bit of math pretty quickly, we get 29 over the square root of 73 miles an hour. Not a particularly large value, but of course these people aren't in cars, they're just walking. Okay, now our next problem is the typical cone. And I feel like I really have to just hit the cone because this is one that is sort of our classic problem. We have our cone, and of course, as it fills up, it generates these nice little right triangles that are actually, in fact, similar. So in the story, the cone whose vertex is down has a height of 20. The height is 20, and its radius is 4. And I'm setting that up because I want to demonstrate that the ratio of the height to the radius is always 5. So we could kind of set this up to make a relationship, which is very, very helpful in these problems. Now, as the story comes in, again, we could go ahead and put that this whole value is 20. This value up here was 4. Those are, in fact, constants because that value is not going to change. But this h and this r right here, in fact, would be changing according to this relationship. We are given in the story that dV dt equals 8 cubic centimeters per minute. And they want to know what is the rate of change of the height and the radius at a snapshot of 10 centimeters. In other words, when it's halfway up the thing. Now, that doesn't mean it's halfway full because there's a lot less volume at the bottom of the cone than there is at the top of the cone. So we're going to start with our volume being 1/3 pi r squared h. Now we have a couple of options. We could actually get rid of h and turn it into r, or get rid of r and turn it into h. In this case, it doesn't really matter because they want to know both rates of change. So I think the easiest one would be to plug in h in terms of r and make this 5r right here. So we're going to replace h with 5r. That's going to give me a brand new equation of 4/3 pi r cubed, or 5/3 pi r cubed. Glitched and said the sphere equation for a second there, huh? So we are ready to go. dV dt equals 5 pi r squared times dr dt, because of course we know at this particular moment the 3 times the 5/3 is going to cancel out and make the 5. We go through the process. We need to know some little piece here because dV dt is given to be 8. 5 pi is a constant. We're looking for dr dt, but we've never found that snapshot of r. So let's go over here and figure that out. Our snapshot. It says when the height is 10, I guess that means that the radius at that moment is 2. So if we could plug in 2 squared, which is 4, we get that 8 equals 20 pi dr dt's. We could divide both sides across, and we're going to find, of course, that dr dt equals 8 over 20 pi. Of course, those are really, really nicely divisible. And so something feels really, really weird to me about that problem, but it's okay. 8 divided by 20, both divisible by 4. So we're going to get 2 over 5 pi, and that would be in centimeters per minute. And then if we look back over here, we could say that if h is 5r, then we could say that dh dt equals 5 times dr dt. And since we already know what dr dt is, we just need to take 5 times 2 over 5 pi, and that's going to give me the 5's cancel. 2 over pi centimeters per minute would be our dh dt. Again, it is a word problem, so if we're being very formal, we would write a little statement that says, hey, these are true, but only specifically at the moment in time when the height is 10 centimeters. Again, this 29 over root 73, that only happens specifically at 4 p.m. Any other moment in time, that answer would be different, but we have found the right answer at that snapshot in time. Then my last question is talking about the fact that we have a balloon over here that's rising, and some little observer is sitting down here and looking at it and seeing that the angle of elevation is changing at 14/100ths of a radian per minute. And then there's this little snapshot, because obviously pi over 4 is not a constant if the balloon is in fact rising. So what I want to do is look at what trig ratio would tie these concepts together. I don't care how far the observer is from the balloon. All I want to know is how fast they're rising, and I know that the observer is standing 500 feet away from the launch point. So the trig ratio that fits very nicely is going to be the tangent of theta. So we have that information. And so we could, I guess, go ahead and go for it and say then that that would be secant squared theta d theta dt equals 1/500th of dh dt. Because remember, the 500 is just a constant. Now in this problem, dh dt is actually what we're trying to find. That's our question. D theta dt, we were actually given in the problem. This is 0.14 rads per minute. So I guess I'll put that one in right now. But I've never taken the time to find out what this is. But at pi over 4, again, it doesn't look like it because this is not the snapshot that we have. But if it's pi over 4, that's exactly 45 degrees, which makes this side 500. And if these sides are both 500, this is a special right triangle, making the hypotenuse 500 over root 2. Now, the nice thing is, if we were looking at it, this is actually a special right triangle. We wouldn't even need the triangle. We should know this from our unit circle. We should know that the cosine of 45 degrees, or pi over 4, is root 2 over 2. So the cosine squared should be 2 over 4, also known as 1/2. But that makes the secant squared a very, very easy number, which is 2. And so if we go through just a little bit further, we're going to have 0.28 on this side equals 1 over 500 dh dt. And so let's multiply both sides by 500, and we get 140 feet per minute. And that is my last problem that I intended to do for this particular video. But again, notice I use special right triangles, but we could have had the same information right off of the triangle. We would have just dealt with larger numbers that had to be simplified. Okay, hey, I will see you back in class.